For the last few weeks of the semester, we're going to be switching gears a bit. Up to now, whenever we've seen a new type of problem, our goal has been to figure out how to solve it efficiently. But starting today, when we see a new problem, our goal will be to prove that it is hard. Specifically, we will aim to classify problems based on whether we think there can or can't exist an efficient algorithm to solve them. But to set the stage, we need to define what sorts of problems we are considering. Most of the problems we have seen and written algorithms for can be classified as decision problems, optimization problems, or search problems. A decision problem is one where we are trying to produce a Boolean output, like true-false or yes-no. Examples of decision problems include connectivity, where we were trying to decide whether T was reachable from S in a graph, and the homework extra credit problem, where you were trying to decide whether a particular collection of coins was canonical. Optimization problems include any of the examples where we were trying to minimize or maximize some numerical value. So examples include distance in a graph, where we're trying to figure out the length of the shortest path between two vertices, and scheduling problems, where we were trying to find the largest number or highest value of jobs that we could accept. Search problems are ones where we are trying to find some object to output other than just a Boolean or numerical value. And examples include finding the cheapest path from S to T, where we are returning a sequence of vertices, or pretty printing a text, where we are trying to find the places to put new lines and output the actual rendering of the story. The reason for separating these types of problems is that when we talk about computational complexity and comparing the difficulty of different problems, it works much better to compare problems within these classes. Comparing search problems to other search problems is, in general, much more effective than comparing search problems to decision problems. But it turns out that for a huge fraction of the problems we've studied, some version of the problem can be formulated within each of these classes. We've seen this already when talking about dynamic programming, where for each of our algorithms, there was first the calculation of optimal value, and then the saving of the choices that led to optimal value, where if all we were interested in was the numerical value, we were solving an optimization problem, but if we actually wanted to know how we got there, that was answering a search problem. And so often the decision or optimization or search formulations of the same problem are very closely related. But let's also think about some specific examples, and for the minimum spanning tree and max flow problems, think about what it would mean to formulate those as a decision or optimization or search problem. Our standard formulation of the minimum spanning tree problem would be classified as a search problem, where our goal is to produce the collection of edges that is a spanning tree with minimal weight. But because we are trying to minimize weight, there is a very natural optimization problem formulation here, which is to ask, what is the smallest possible weight of any spanning tree? And the natural decision problem corresponding to this optimization is to ask whether there is a spanning tree with cost below some threshold. For max flow, our standard formulation of the problem was to find a flow function with maximal value, and so that would qualify as a search problem. But since we are trying to maximize the value of the flow, the natural optimization problem is how much flow could be pushed from S to T. And in terms of a decision problem, we might be interested in whether it is possible to send a given amount of flow from the source to the sink. And so for many of the problems that we've studied, we can naturally formulate search or optimization or decision versions of those problems. So to simplify our discussion of the relative difficulty of different problems, we will focus in on decision problems and translations between different types of decision problem. And this leads us to the formal definition at the core of our study of problem hardness, which is a polynomial time many-one reduction. Like the reductions we have been using all semester, a polynomial time many-one reduction translates an instance of one problem into an instance of another problem. But we are working here specifically with decision problems, and so both the original problem P and the translated problem Q need to be decision problems. And when we say that decision problem P reduces to decision problem Q, that means there is some algorithm that runs in polynomial time that translates any instance of problem P into an instance of problem Q. And we specifically want that the answer to the translated problem is yes, if and only if the answer to the original problem was yes. So whenever the answer to the original decision problem was yes, after we translate the problem, the answer to the new decision problem will also be yes. And whenever the answer to the original decision problem was no, the answer to the translated decision problem is no. We require that this reduction algorithm run in polynomial time, and that's why we have a subscript p on our reduction symbol. And we use the symbol less than or equal to because when we have some way of translating every instance of problem P into an instance of problem Q, that means problem Q is at least as difficult as problem P. Specifically, if we have a reduction from problem P to problem Q, that means we can translate any instance of problem P into an instance of problem Q such that the answer is the same. And so if we had a polynomial time algorithm for solving problem Q, we would also have a polynomial time algorithm for solving P, because for any instance of problem P, we could first run it through our reduction, which translates to problem Q, and then run it through our algorithm for Q, which will give us a yes or no answer. And since the answer of the translated problem is the same as the original answer, this would solve problem P. And as long as both the algorithm for Q and the translation algorithm run in polynomial time, overall we have a polynomial time algorithm. So if A is an algorithm for Q, then we can run A on the output of M, where M is producing an instance of problem Q. And so the composition of A and M is a function that takes an instance of problem P and outputs yes or no. So as long as the translation and solving Q steps are correct and efficient, the algorithm correctly and efficiently solves problem P. But this is the same way of using reductions that we've seen before. If we have a way of solving problem Q, then we can solve problem P by translating and then running our algorithm for Q. What's far more useful to us, and the source of the less than or equal to sign here, is the contrapositive of this statement. If we have a polynomial time reduction from problem P to problem Q, that means that if there isn't a polynomial time algorithm for P, there cannot be a polynomial time algorithm for Q. We've already proven this statement because it's the contrapositive of the statement we already proved, but we could also think of a proof by contradiction here. If there can't be a polynomial time algorithm for P, but we know a polynomial time way of translating to Q, if we had a polynomial time algorithm for Q, then composing those two would give us a polynomial time algorithm for P, which contradicts our claim that there wasn't a polynomial algorithm for P. So this means that if we have a polynomial time reduction from problem P to problem Q, if we can also show that problem P is hard to solve efficiently, this would imply that problem Q is also hard to solve efficiently. And that's why we use a less than or equal to sign here, because if P is hard, Q must also be hard. So Q is at least as hard to solve as P. So now that we've defined polynomial time many-one reductions between decision problems, let's take a look at some examples of decision problems and think about how to reduce from one to another. Of particular note, all of the problems defined here are ones that I do not know how to solve efficiently. So the algorithms that we are going to be writing are to translate one problem to another, but these algorithms are not solving any of the problems. Giving a polynomial time reduction just means giving a way to translate one problem into another. If we also have an algorithm that solves the target problem, then, by number one, we can solve both problems. But a lot of the time, when we are thinking about hardness, we will be translating between problems that we don't actually have efficient algorithms for, because we want to use fact 2, that if problem P is hard, problem Q must also be hard. We have 3 problem definitions here, and in a moment we'll talk a bit more about each of them to build some intuition. But our eventual goal is to give a polynomial time reduction from vertex cover to independent set, and another polynomial time reduction from vertex cover to set cover. And so, before I erase it, we should think about what each of these reductions means. If we can reduce vertex cover to independent set, that means if we have an efficient algorithm for independent set, we will also have an efficient algorithm for vertex cover. On the other hand, if we could prove that there isn't an efficient algorithm for vertex cover, that would also prove that there isn't an efficient algorithm for independent set. Likewise, when we reduce vertex cover to set cover, if we can find an efficient algorithm for set cover, that would give us an efficient algorithm for vertex cover. But if we could prove that there isn't an efficient algorithm for vertex cover, that would also prove that there is no efficient algorithm for set cover. In the vertex cover and independent set problems, we are given an undirected graph. If we have an undirected graph, then a vertex cover of that graph is a subset of the vertices such that for every edge in the graph, at least one end of the edge is in the vertex cover. So we can pick out some of these vertices and try to make sure that every edge in the graph is covered by some vertex. So the set of vertices that I have highlighted in red here constitutes a vertex cover of this graph because for every edge, at least one end of the edge is incident on a vertex that is part of our red subset. It's okay to have both ends of an edge be in our subset, but we're not allowed to have any edges where both ends of the edge are outside of our set. And so the decision version of the vertex cover problem gives us an integer k and asks, is there a vertex cover containing k vertices? In the independent set problem, we are also given an undirected graph, but here our goal is to choose a subset of the vertices such that no two vertices we choose are connected by an edge. In our example graph, the following vertices are an independent set. So for each of the vertices I have highlighted in blue, it is not adjacent to any other blue vertex, and so we have a set of vertices that are all independent. And so the decision version of the independent set problem gives us an integer k and asks whether there is an independent set in the graph of size k. And hopefully from this example that I've drawn, you're starting to get an idea of the connection between the independent set and vertex cover problems. So let's figure out how we could do a polynomial time reduction from vertex cover to independent set. To prove that one problem is polynomial time reducible to another, there are 3 steps. First, we have to give an algorithm that translates our source problem into our target problem. Then we have to prove that our algorithm runs in polynomial time. And finally, we have to prove that for any instance of our original problem, when we run it through our translation algorithm, the answer is preserved. The original instance had an answer of yes, if and only if the translated instance has an output of yes. So step 1 is to describe our algorithm, and our algorithm takes as input an instance of the vertex cover problem. So we are given a graph and an integer. And it produces an input to the independent set problem, which is also a graph and an integer. And in this case, our graph for the translation to independent set is the same as the graph we were given for the original vertex cover problem, but the integer that we are giving to independent set is different. Specifically, we take the value of k that we were given for vertex cover and we subtract it from the number of vertices, and that gives us k prime, the integer we will give as input for independent set. The reason we do this is that if the red nodes are a vertex cover, then all but the red nodes will be an independent set. So if there is a size k vertex cover, then the remaining vertices will be a size n minus k independent set. Our next step is to prove that our translation algorithm runs in polynomial time. All we had to do to translate was subtract k from the number of vertices. So this is actually a constant time algorithm to translate from a vertex cover instance to an independent set instance. And now we have to prove that this translation preserves the answer. That is, the answer to the original vertex cover problem was yes, if and only if the answer to the new independent set problem is yes. And so we'll split this if and only if into the two directions. So first we want to show that if the original graph had a size k vertex cover, then the new graph will have a size n minus k independent set. So if the answer to the original problem was yes, then we have a size k subset S, and we know that for every edge in the graph, at least one end of that edge is a vertex in S. So if we take any vertex that's not in S, all of the edges that that vertex has must have their other end in S. And so no two vertices in the rest of the graph can be adjacent. And so if we take all of the vertices that are not in S, those vertices are all independent. And so we have an independent set of size, number of vertices, minus the size of S, which was k. What remains is to show that if the answer on the translated instance is yes, then the answer on the original instance is yes. And it's worth noting that this is the contrapositive of saying that if the original answer was no, then the translated answer will be no. And for some proofs, that version of the if and only if might be easier to prove. But here we can think about an independent set in the same graph that we started with. So if we have a size k prime independent set, then we know that none of the vertices in the independent set are adjacent, so there cannot be any edge that has both ends in S prime, which means that if we take all of the vertices that are not in S prime, every edge must have at least one end in that set of vertices. So v minus S prime is a vertex cover, and if the size of the independent set was k prime, then the size of the vertex cover is k. So we have that whenever the answer to the translated independent set problem is yes, the answer to the original vertex cover problem was also yes. So we have proven that vertex cover is polynomial time reducible to independent set. Our third example problem that I don't know how to solve efficiently is known as set cover. Here, rather than being given a graph, we are given a set U for universe, and then we are given another set which consists of subsets of the universe. So we are given a collection of subsets, and among those subsets, if we can select some, that when we union them all together, we get the original set, those subsets are a set cover of our universe U. So in the decision version of the set cover problem, we are given U and the collection of subsets and an integer k. And the question is whether we can pick k of the subsets such that their union is the original set. Once again, our goal is to give a polynomial time reduction from vertex cover. So we want to take an instance of the vertex cover problem where we are given a graph and translate it into an instance of the set cover problem where we are given a set and a collection of subsets. Our translation takes a graph and an integer representing a vertex cover problem, and it produces an instance of a set cover problem. So it produces a set U, a collection of subsets of U, and an integer. Our universe for the set cover problem is all of the edges from the vertex cover graph. Then for every vertex in the graph, we define a subset, which is all of the edges incident on that vertex. And then our collection of subsets is the subset for every vertex. And we are looking for a set cover of the same size as the vertex cover we were seeking in the graph. The time it takes to construct our instance of set cover is linear in the size of the original problem, because for every edge, it has to go in 2 of the subsets, and for every vertex, we have to build a subset. But linear time is clearly polynomial, so we have succeeded in providing a polynomial time translation. And now all we have to do is prove that our translation preserves the answer. Again, we will break this down into the if and only if directions. So first we want to show that if there was a size k vertex cover, then there will be a size k set cover. If we have a subset of the vertices that covers all the edges in the original graph, then we can take all of the subsets corresponding to those same vertices to build a collection of subsets that covers U. So for each vertex in the vertex cover, all of the edges that are incident on that vertex must be in SV. So SV covers all of the elements of U corresponding to edges incident on V. And so every edge that is covered by C corresponds to an element covered by T. And since the number of subsets we picked was equal to the number of vertices we picked, we have a set cover of the same size as the original vertex cover. The reasoning for the other direction is quite similar. If we have a set cover here, then each of those subsets corresponds to a vertex, and so the elements covered by those sets will correspond to edges covered by those vertices, and we will have a vertex cover of the same size in the graph. And once again, the size of the vertex cover is equal to the size of the set cover. So if there is a size k prime set cover, then there was also a size k vertex cover. And we've shown that if the answer to the translated problem is yes, then the answer to the original problem was yes. Overall, we've now given a polynomial time reduction from vertex cover to set cover. And so between these two reductions, we've shown that if we can efficiently solve either set cover or independent set, that would give us an efficient algorithm for vertex cover. And we know that if we can show vertex cover to be a hard problem, that would also imply that both independent set and set cover are hard problems as well.